Chebyshev polynomials are another important family of special curves used in mathematics, physics, and computer science. They may sound like a complicated invention, but their purpose is surprisingly practical. They help us create very accurate approximations of functions while keeping errors as small as possible. In other words, if you want to represent a complicated curve using simpler building blocks, Chebyshev polynomials give you some of the best building blocks you can choose. They are named after the Russian mathematician Pafnuty Chebyshev, who studied how to minimize errors when approximating functions. His discovery turned out to be so powerful that Chebyshev polynomials now appear everywhere, from numerical algorithms to digital signal processing, computer graphics, and even the design of electronic circuits. A ladder of best-behaved curves. Just like Legendre, Hermite, and Laguerre polynomials, Chebyshev polynomials form a sequence of curves. The first one is simple and smooth. The next one has one wiggle. The next has two wiggles. Then three, then four, and so on. Each polynomial in the sequence adds more oscillations. But what makes Chebyshev polynomials special is the way these oscillations are arranged. They spread themselves out in the most balanced way possible. The peaks and valleys occur symmetrically at very specific positions and with nearly equal height. This structure gives them incredible stability. Think of them like the most fairly stretched wave patterns you can draw on a fixed interval. No part of the curve is allowed to behave wildly or dominate the others. Why their oscillations matter, most polynomial curves tend to blow up near the edges of the interval they cover. If you've ever tried to approximate a function using ordinary polynomials, you may have seen the edges of the curve swing upward or downward in a dramatic way. This is called Runge's phenomenon, and it can ruin the accuracy of numerical methods. Chebyshev polynomials avoid this problem beautifully. Their oscillations are arranged so carefully that no sudden, extreme behavior develops at the edges. Instead, they maintain a calm, controlled pattern across the whole interval. This is why they are the foundation of many modern approximation techniques. The king of approximation. Minimizing maximum error, one of the most important properties of Chebyshev polynomials is that they provide the best possible polynomial approximation to a function if your goal is to keep the maximum error as small as possible. In simple terms, when you try to approximate a curve and you want the approximation to be as fair and balanced as possible so that no point is more wrong than the others, Chebyshev polynomials give you the optimal solution. This is known as the Chebyshev minimax property, which means the error oscillates evenly and never spikes in any particular spot. Because of this, Chebyshev polynomials are the backbone of Chebyshev approximation, Chebyshev filters, and many advanced numerical methods. Chebyshev polynomials are extremely useful in numerical computation for several reasons. 1. Chebyshev nodes. If you take the special points where Chebyshev polynomials have their extreme values, you get what are called Chebyshev nodes. These nodes are widely used in interpolation to avoid the problem of wild swings at the edges. Interpolating a function at Chebyshev nodes produces much more accurate and stable results than using evenly spaced points. 2. Chebyshev series. Just like you can represent a function using sine waves or Legendre polynomials, you can represent it using Chebyshev polynomials. This is called a Chebyshev series, and it often converges extremely fast, meaning you need fewer terms to reach high accuracy. 3. Root finding and solving equations. Many numerical methods use Chebyshev polynomials to speed up convergence and reduce errors. 4. Chebyshev filters in electrical engineering and signal processing. Chebyshev filters use the unique properties of these polynomials to design circuits that have a very specific and controlled frequency response. In computer graphics, Chebyshev polynomials are used to approximate curves and surfaces with minimal distortion. Since modern graphics rely heavily on numerical approximation, whether it's shading, simulation, or geometry, they often use Chebyshev-based techniques. Game engines, rendering pipelines, and scientific visualization tools all benefit from the stability and efficiency provided by Chebyshev polynomials. Interestingly, Chebyshev polynomials behave a lot like cosine waves, but in polynomial form. This gives them a smooth, wave-like structure that works extremely well in applications involving oscillations or periodic patterns. What's surprising is that even though they are polynomials, They mimic the behavior of trigonometric functions in a way that preserves stability and reduces error. This connection to wave shapes is a big reason they show up in signal processing and spectral methods. Like Hermite, Laguerre, and Legendre polynomials, Chebyshev polynomials are orthogonal, meaning each polynomial captures a unique pattern. No polynomial overlaps with the information in another. You can combine them cleanly to build more complicated curves. This makes them ideal for breaking down functions into manageable components, each term contributing its own distinct shape. Even without equations, we can appreciate their importance. They create the most stable approximations. They avoid the wild oscillations that plague ordinary polynomials. They give us optimal accuracy with minimal effort. They combine wave-like behavior with polynomial structure. They are essential in numerical algorithms, filtering, graphics, and engineering. They are one of the most widely used mathematical tools in computational science, even though many people never hear their name. Conclusion: Chebyshev polynomials are beautifully balanced, wave-like curves that provide the best possible way to approximate complicated functions using simple polynomials. They avoid distortions, minimize errors, and offer unmatched stability. From digital filters to numerical algorithms and computer graphics, they form one of the most powerful and reliable toolkits in modern applied mathematics.